Hello everybody. In this video we're going to continue with Chapter 11, Probability. Specifically we're going to go into Section 11.3, Operations with Events. So in the previous section we worked with example 11.5, which said, when people create codes for their smartphones, the first digits follow distributions very similar to this one, and they gave us this table. Then they asked us to find some probabilities. We're going to focus on B and C. So what is the probability of event B? And we said that the probability of event B, which is first digit is more than 5, is equal to the probability that it's 6 plus the probability that it's 7 plus the probability that it's 8 plus the probability that it's 9. And then for event C, the first digit is an odd number. We said that the probability for C is equal to the probability that it's 1 plus the probability that it's 3 plus the probability that it's 5 plus the probability that it is 7 and the probability that it is 9. But then what I want to focus on is on part B, number 3, which says find the probability that the first digit is an odd number or a number larger than 5. So we said that this is equal to the probability of B union the probability of C. And then we said that this was equal to probability that it's 1 plus probability that it's 3 plus probability that it's 5 plus probability that it is 6 plus probability that is 7, that it is 8, and that the first digit is 9. So one thing we didn't explain is that basically what we're doing here is saying that the probability of B union C equals the probability of B plus the probability of C minus the intersection of the probabilities of B and C. So what is the intersection of B and C? Well, we can see it here in this Venn diagram. The intersection of sets B and C are numbers 7 and 9. Notice that I did not repeat 7 and 9, but 7 and 9 belong to both sets because they're not mutually exclusive. 7 and 9 are both odd, and they are also larger than 5. So in general, we can say that the probability of A or B, which is the same as saying the union, is equal to the probability of A plus the probability of B minus the probability of their intersection, which is the same to say probability of A and B. So what we have in A and B is 7 and 9 in this particular case, and we would have to subtract it. But if the events are independent from each other, then the probability of A union B would simply be probability of A plus probability of B, since the probability of their intersection would be 0. Two events, A and B, are independent if knowing that one of them occurs does not change the probability that the other occurs. The multiplication rule for independent events is if two events, A and B, are independent, then the probability of A and B, or the intersection of A and B, is probability of A times probability of B. Now here it is very important to note that we must not confuse independent with mutually exclusive. Mutually exclusive means that if one of the events occurs, then the other one does not occur. While independent means that knowing one of the events occurs does not influence whether the other one occurs. So let's focus now on example 11.9. And it says, there's a traffic light just before I get to school. The probability that I find the light green is 0.3. Find the probability that I find it green on A, 2 consecutive days. So for letter A, finding it green 2 consecutive days is the same as saying the probability that we find it green on day 1 times the probability that we find it green on day 2. So this is going to be 0.3 times 0.3, and this is 0.09. For letter B, it says every school day 1 week. So that means 5 times in a row. So it would be the same as saying 0.3 to the 5, and this is equal to 0.00243. So now let's focus on example 11.10. And it says, computers bought from one company require repairs quite frequently. It is estimated that 17% of computers bought from one of these companies require one repair during the first month after purchase. 7% will need repairs twice during the first month, and 4% require 3 or more repairs. Letter A, find the probability that a computer chosen at random, very important word, from this producer will need 1. No repairs. So let's start with that. So notice that the probability of no repairs is actually the complement of the probability of needing some repair. So the probability of no repairs would be 1 minus the probability of some repair. So notice that we had 17%, so that's 0.17. That is that it'll break down once, plus 0.07, the probability that it'll need to be repaired twice, plus 0.04, which would be the probability of it requiring 3 or more repairs. So then this would equal 1 minus 0.28, and this is equal to 0.72. For part 2, it says the probability of no more than one repair. So that means one or less, right? So that means the probability of 0 plus the probability of 1. So notice that I'm using addition here because all these events are disjoint. That's why we can use this rule. So the probability of 0 is 0.72, and the probability of 1 is 0.17. And if we add this, it's going to be 0.89. So 89% chance that you will need no more than one repair. For number 3, some repair. Well, some repair is the 0.28 that we found in the first problem, which was the addition of requiring one repair, 2 or 3 or more. So that would be 0.28 or 28% chance. So now let's focus on part B. So for part B, it says if you buy 2 such computers, find the probability that 1, neither will require repair. So remember that we found that the probability of no repair is 0.72. Now, notice that repairs on the 2 computers are independent from one another, so the multiplication rule can be used. That means that the probability that neither computer will require or need repair is going to be 0.72 times 0.72. And this is equal to 0.5184. So about 52% chance that neither will need repair. Then for part 2, they want us to find the probability that both will need repair. And this involves the probability of some repair, which we said before was 0.28. So that means that the probability of both of them requiring some repair would be 0.28 times 0.28, which is going to give us 0.0784. So now we're going to focus on conditional probability. And let's start by doing example 11.11. And it says, a public health department wants to study the exercise habits of high school students. They interview 768 students from grades 10 to 12 and ask them about their exercise habits. They categorize the students into the following three categories: frequent exercisers, occasional exercisers, and non-exercisers. The results are summarized in a table. If a student is selected at random from this study, so that's from the whole group of students, find the possibility that we select a female. So it's about finding the probability that we select a female from the whole group. So this is simply going to be the total females, which is 354, divided by the total amount of students, 768. And this is going to equal 0.461. For part B, a male frequent exerciser. So male and frequent exerciser would be 127 out of the total 768. And if we do the division here, it's going to give us 0.165. Then for part C, a non-exerciser. So regardless of the gender, somebody that does not exercise. So the total non-exercisers are 403. Therefore, it's going to be 403 out of 768. And this is going to give us 0.525. Given any events A and B, the probability that both events happen is given by P A intersection B, which is equal to the probability of A given B times the probability of B. So now let's focus on example 11.12. And it says 6 green toys and 4 red toys, identical apart from color, are placed in a container. A child is asked to select 2 toys at random. What is the probability that the child chooses 2 green toys? Okay, so let's use a tree diagram for this problem. So notice that first the child has to select a red toy or a green toy. And the probability of selecting a red toy is going to be 4 out of 10 because there's 10 toys total. And the probability of selecting a green toy is 6 out of 10. Then after this, the tree diagram splits up into 2 again, where you have a chance of picking red or green, and then again, red or green. But now the probability of picking red again is going to be 3 out of 9. Green would be 5 out of 9. Same here, 3 out of 9 and 5 out of 9. So the probability of picking green and green is going to be 6 out of 10 times 5 out of 9. And this is going to equal 1/3 or 33%. When the probability of B is different from 0, the conditional probability of A given B is equal to the probability of A intersection B over the probability of B. Notice that this is just a rearrangement of the formula we saw in the past example. So now let's focus on example 11.13. And it says, in an experiment to study the phenomenon of color blindness, researchers collected information concerning 1,000 people in a small town and categorized them according to color blindness and gender. Here is a summary of the findings, and they give us this table. What is the probability that a person is colorblind given that the person is a woman? So notice that this is the probability that a person is colorblind given that it is a female. So this is going to be the probability of the intersection of colorblind and female over the probability of it being a female. But notice that this is just the same as saying the number of events where we have a colorblind female over the total amount of females. And notice that it's going to be 2 because we have 2 females that are colorblind over the total number of females, which is 490. So this is going to equal 0.004. So next we're going to look at example 11.14, and it says, one national airline is known for its punctuality. The probability that a regularly scheduled flight departs on time is 0.83. The probability that it arrives on time is 0.92. And the probability that it arrives and departs on time is 0.78. Find the probability that a flight, A, arrives on time given that it departed on time. So this is the probability that it arrived on time given that it departed on time. So remember that this is going to be the probability of A intersection D over the probability of D. So this is simply 0.78 divided by 0.83, and this gives us 0.94. For B, the probability that a flight departs on time given that it arrived on time. So this is the probability of D given A, which is the probability of the intersection of D and A over the probability of A. And then this is going to be 0.78, but this time divided by 0.92, which is going to give us 0.85. So now we're going to talk about independence. Two events are independent if learning that one occurred does not affect the chance that the other occurred. That is, that the probability of A given B is equal to the probability of A and vice versa. This means that if we apply our definition to the general multiplication rule, then the probability of A intersection B is equal to the probability of A given B times the probability of B, which is the probability of A times the probability of B. So this is the multiplication rule for independent events that we studied earlier. These results give us some helpful tools in checking the independence of events. So let's take a look at example 11.15, and it says, take another look at example 11.14. Are the events of arriving on time, A, and departing on time, D, independent? So we can verify this using two different methods, right? So the first method would be to check if the probability of A is equal to the probability of A given D. And if you recall, the probability of A was 0.92 and the probability of A given D was 0.94. And since these two are not equal, the events A and D are not independent. Alternatively, we can check if the probability of A intersection D is equal to the probability of A times the probability of D. Remember, we were told that the probability of A intersection D is 0.78. Then this would have to equal the probability of A, which is 0.92, times the probability of D, which is 0.83. But this gives us 0.76. Therefore, these are not equal. And that means that the events A and D are not independent. Okay, so now let's focus on example 11.16. And it says, if a doctor suspects that a patient is lactose intolerant, they might give the patient a breath test or a blood test or both in order to make a diagnosis. A study found the following results in a particular country. 81% of the patients suspected to be lactose intolerant were given a breath test, 40% a blood test, and 25% both tests. Letter A. Find the probability that a patient suspected to be lactose intolerant is given 1. At least one test, 2. Exactly one test, and 3. No test. So for this, we're going to use a Venn diagram because we have the condition that there are people that are taking both tests. So that means that there's an intersection between both of those events. The probability of taking the blood test is 40%, but we have to consider that taking only the blood test is going to be 15%. That is 40 minus the 25, because there's 25% to take both tests, as we can see here. Likewise, with breath, we have 81%, but only breath would be 56%. So let's focus on number 1, the probability of at least one test. So that's the same as saying the probability of the blood test plus the probability of both tests plus the probability of a breath test. And this is going to give us 0.96. Now, for part 2, exactly one test would be the probability of receiving the blood test only plus the probability of only receiving a breath test. And this is going to give us 0.71. For part 3, no test would be 1 minus the probability of at least one test, right? The complement of that. So this is going to be 1 minus 0.96, which is 0.04. Now let's focus on part B. So for B, they ask, are the events giving the patient a breath test and giving the patient a blood test independent? So if these events are independent, we would have that the probability of both tests should equal the probability of the breath test times the probability of the blood test. And this is going to be 0.81 times 0.40, which is equal to 0.324. But this is not equal to the 0.25 that represents the intersection between blood test and breath test. Therefore, the events of receiving a breath test and a blood test are not independent. So next we have example 11.17, and it says, Jane and Kate are longtime friends and frequently play tennis together. When Jane serves first, she wins 60% of the time. Likewise, when Kate serves first, she wins 60% of the time. They alternate the person serving. They usually play for a prize, which is a chocolate bar. The first one who loses on her serve will have to buy the chocolate. Jane serves first. Part A. Find the probability that Jane pays on her second serve. So for this, we're going to use a tree diagram. So notice that Jane serves first. So Jane can either win or Jane can either lose. Her probability of winning is 0.6. Therefore, the probability of losing is 0.4. After this, we have that Kate serves. So Kate can either win or Kate can either lose. And again, it's going to be 0.4 and 0.6. After this, Jane serves. So Jane can either win or Jane can lose. And again, 0.4 and 0.6. And this continues on, right? So next, we would have Kate winning or Kate losing. So 0.4, 0.6, and so on. So they want us to find the probability that Jane pays on her second serve. That is, that she loses on her second serve. So notice that several things would have to happen. Jane would have to win her first serve, then Kate would have to win her first serve, and then Jane would have to lose her second serve. So that means that it would be the probability of Jane winning times the probability of Kate winning her serve times the probability of Jane losing her second serve. And this is going to be 0.6 times 0.6 times 0.4, which gives us 0.114. For part B, find the probability that Jane eventually pays for the chocolate. So notice that Jane could lose in any of her serves, right? So she could lose in her first serve. So the probability that Jane pays would be the probability of Jane losing in her first serve, or the probability that Jane wins, and then the probability that Kate wins, and then that Jane loses. Or, and this continues on, right? The probability that Jane wins, and then Kate wins, and then Jane wins again, but then Kate wins, and that Jane loses. And so forth. So continuing over here, notice that mathematically this means 0.4 plus 0.4 times 0.6 squared plus 0.4 times 0.6 to the 4, etc. So this appears to be the sum of an infinite geometric series with 0.6 squared as a common ratio and 0.4 as the first term. So with this, we can say then that the probability that Jane pays is going to be equal to the first term, 0.4, divided by 1 minus the common ratio, 0.6 squared, and this is going to equal 0.625. Then for part C, find the probability that Kate pays for the chocolate. Notice that this would just be the complement of B. So the probability that Kate pays is going to equal 1 minus the probability that Jane pays, which was 0.625. So this will be 0.375. We could also have answered using an infinite geometric series, but I will leave that to you as an exercise. So finally, we're going to do example 11.18, which is the last one on this video. And it says, the figure here shows a target for a dart game. The radius of the board is 40 centimeters, and it is divided into 3 regions as shown. You score 2 points if you hit the center, 1 point for the middle region, and 0 points for the outer region. Part A, what is the probability of scoring a 1 with 1 attempt? So this is geometric probability. Notice that the area for 1, which is this white section, is going to be equal to the area of what would be the white circle. So that's going to be 20 squared times pi minus the area for the green circle, so 10 squared, over the total area, which is pi times 40 squared. So if we solve this, it's going to give us 3 out of 16. For part B, they ask what is the probability of scoring a 2 with one attempt. So that would be the green area, pi times 10 squared, divided by the whole area, pi times 40 squared. So this is going to give us 1 over 16. For part C, it says how many attempts are necessary so that the probability of scoring at least one 2 is at least 50%. So here we have to take several things into consideration. First, let the number of attempts be equal to n. Then the probability of at least 1 2 is going to be 1 minus its complement, which is the probability of no 2 in n attempts. So this is going to be 1 minus 15 over 16, because it's the complement of 1 2, and this is no 2. So this to the power of n. And then it says that this probability has to be at least 50%. So that means that this has to be greater than or equal to 0.5. So notice that this implies that 15 over 16 to the power of n would have to be less than or equal to 50%. Why? Well, because notice that we are subtracting it from 1. So this is what we have to solve, and we use logarithms for this. So notice that this is the same as saying n times the natural logarithm of 15 over 16 less than or equal to the natural logarithm of 0.5. And then this is simply going to be that n will be greater than or equal to the natural logarithm of 0.5 divided by the natural logarithm of 15 over 16. Now, why did we switch this? Because the natural logarithm of 15 over 16 is negative. And then finally, we're going to get that n will have to be greater than or equal to 10.74. So that means 11 attempts.